Good morning to everyone. In today's video, we are going to see the coefficient of coupling. So, when we go for a magnetic circuit, when you go for a magnetic circuit, if it is having a two or more coils, the inductance of the one coil will be affected the inductance of the other coil, which will be given by using your coefficient of coupling. Okay, so the amount of coupling, whatever the amount of coupling between the inductively coupled coils, which we are going to express in terms of your coefficient of coupling. Okay, we will see what the values and how it going to be derived in this video. Okay, for perfect coupling, that means the complete whatever the flux. Okay, to develop your inductance we require the flux. So whatever the flux of the first coil is completely transferred to the second coil, then this k value will be equals to the 1. Okay, we will see that. for time being consider two inductively coupled coils. Okay, consider two inductively coupled coils. Here, based upon your dot notation, your mutual inductance is depending. For example, as per the dot convention, when the two coils, the both the currents, in the two coils, both the currents are enters or leaves through the dot, then the mutual inductance will be considered as positive. Otherwise, if in one coil the current is entering through the dot, if in one coil the current is entering through the dot, in another coil the current is leaving through the another dot. That means here I am changing the direction. If current is leaving through the dot, at that time the mutual inductance will be the negative. So if it is in positive, that means the mutual inductance is positive, we say that it is magnetically aiding circuit. If M value is negative, we say that it is magnetically opposing circuit. Okay, so based upon that we just derive the voltages across the coil number 1 and coil number 2. Already we discussed this point in our previous video, but at a glance I just want to mention this is the inductance coil number 1. This is the inductance of coil number 1. The voltage across the coil number 1 will be given as V1. Okay, across the coil number 1 it is given as V1. So what is the voltage drop across this coil 1 due to its self inductance? That is mentioned it as L1 di1 by dt. But apart of this self inductance, whatever the flux is flowing, whatever the flux flowing in this coil number 1 is responsible to flow the current in your second coil also, because it is magnetically coupled circuit. These flux lines are moves through this core and cuts the coil number 2 also, and responsible for flowing of the current in the coil number 2. That means the flux in the first coil induces the current in the second coil, that we given it as mutual inductance M, and flows the the voltage will be develops because of your current in the coil number 2. So that gives the total voltage of your first coil. Similarly, for the second coil, the current in the second coil and the self inductance of the second coil, that is self inductances. But the current in the second coil due to that flux will develops and it cuts the first coil. Again the mutual inductance comes into the picture. When you call from one coil to the other, then we go for the mutual inductance responsible for the first current in the first coil. Again the voltage will be develops. So this gives you the voltage equations for magnetically coupled circuit. Okay, these are the voltages for the two coils. we know that the initial current of the coupled circuit will be 0, because it is not, these coils are not electrically charged one, it is starting from 0 onwards. We are considering it as an completely discharged circuits. So the energy storage of the energy storage of these coils will be 0. So the total energy, the total energy given to this system at a time t will be, we know that the energy will be the integration of power for an interval of 0 to t. So the power will be mentioned in terms of voltages and currents. So for two coils we are mentioning it as V1 I1, V2 I2, which depends upon the time, this. So 0 to t. We know the values of V1 and V2. So please replace those values in your equation. I got this one in this format. So whatever this equation, L1, L2, M are time independent variables. L1, L2, M and L2 and are the time independent variables. So try to bring out that from the derivation, whatever the integration is there, try to bring out. Okay, so once I got this one, it will be in the format of integral uv. Okay, it is in the format of integral uv. Try to substitute those values. Okay, try to substitute that equation in the format and try to find out. Okay, so integral di1 dt divided by dt into dt. So this dt will be cancelled out. Whatever the integration and the derivation will be cancelled over. So this term will be the I1 square. The same thing I am written, and the rest of the equation, it will be integral I dt, I1 dt into di1 by dt into dt. So if I try to solve out, it will be form of I square. That means it will be in simply form of I di. Okay, it will be in the form of integral I di. So if I go for the integration of I, it will be the I square by 2. Okay, if I go for the integration, I square by 2. So when I try to solve this, it will be the I square by 2. Similarly for the second equation, it will be the I square, half Li square by 2. And next one, this will be the combination of I1 and I2. It will be the combination of your I1 and I2. So M I1 I2. So if I solve this, so I am not going in detail of each and every step. So the final expression for the energy, is nothing but half Li square plus half L1 I square plus half L2 I2 square plus M I1 I2. Okay, this is for the magnetically aiding circuit, and all the terms are positive, so there is no need to find out for what value it will be the positive or not. So that's why I am considering another circuit, that is magnetically opposing circuit. So instead of positive M, I am considering it as minus M. Now whatever this energy is always a positive value for any value of I1, I2, L1, L2 and M. For that reason, we are considering this energy, whatever this energy equation should be greater than or equal to your 0 for any time. Okay, for whatever the time, it should be greater than or equal to 0. Okay, so I'm just writing the equation once again. Now I'm just adding and subtracting a term M square I2 square divided by 2L1. Okay, I'm just adding and subtracting, then there will not be any issue of the total term. I'm just adding and subtracting for easily converting this expression, okay, for ease of conversion. So when I arranging these terms, half L1 I1 square plus m square I2 square divided by 2L1 minus m I1 I2, and the rest of the terms I'm written. So if you observe this one, I'm just bringing out half, and it will be a square plus b square minus 2ab. That means if I bring out 2 outside, I just multiply it with the numerator and denominator with 2. So denominator 2 is there, I'm just bringing it out. Okay, now it will be in the form of a square, that means root L1 I1 whole square. Okay, next it will be in the form of m I2 root L1 whole square. Okay, so this is minus 2. I just want this one as root L1 I1 into m I2 root L1. So L1 root L1 cancelled, m I1 I2. So now this expression is nothing but your a minus b whole square. So root L1 I1 minus m I2 divided by root L1 whole square. Okay, the rest of the terms I'm just simply written half L2. I just bring out common the I2 square term. So half L2 minus m square divided by L1. Okay, so when I go with these two terms, first term is always positive because it is square. Whether you are having positive value or negative value, whatever may be, your first term will be the positive. So the only condition is your second term should not be a negative value. It should be always positive. That means L2 minus m square divided by L1 should be greater than 0. I'm just rearranging. Then your m value, the m value is less than or equal to square root of L1 L2. Okay, m value is always less than or equal to square root of L1 L2. That means the ratio of actual mutual inductance between the coils, that is m to the square root of L1 L2, is your coefficient of coupling. Okay, so the maximum possibility, that is whatever the self inductance, square root of L1 L2 will be your maximum possibility mutual inductance. Okay, here one thing is clear, your k value is a non-negative number. It always depends upon the value of your mutual inductance but not your current directions, and its value is lies in between. Okay, if m and square root of root over L1 L2 is same, the maximum value will be equals to the 1. Equals to 1, that we termed it as perfect coupling. Okay, perfect coupling. For example, if the distance between the coils is very large and nowhere the flux of first coil cuts the second coil, we say that no inductance will be induces. No current will be flows from first coil to responsibility of due to the first coil to the second coil. That at that time we say that it is not at all coupled. So 0 to 1. But for iron cored couples, maximum chance of coupling will be there. It is around 0.99. For air cooled couples, it will be between the values of 0.4 to 0.8. So by this I can try to conclude the derivation of coefficient of coupling. Thank you.